Okay, welcome all. Bhargav would be a little late, so we shall get started with this session. Um, so today we will leave the floor to Yasholekha and Abhinav, who've done some homework on the gradient descent algorithm. Um, so what Abhinav and Yasholekha are going to do is they're going to share a presentation on how the gradient descent algorithm works. And I mean, it's a standard algorithm used in many contexts, but for the sake of this session, they'll take us through the regression problem and help us understand how gradient descent would help us to figure out the regression coefficients. So over to you, Abhinav and Yasholekha.
Okay, once again, we say I shall share my screen.
And folks, if you have any questions, feel free to stop and ask them.
Okay, got it ready. Okay.
Are you sharing, Abhinav?
Yes, yes. Okay.
Yeah, Naveen.
Yeah. Is my slides are visible?
Yes.
Yes, sir.
Today we are going to see about gradient descent and optimization algorithm widely used in many machine learning algorithms. So today we are going to see it with this in the context of linear regression, as we said. So let's start from the basic. What is linear regression? Let me change the Excalibur. Okay, I have to show something. Yes, I shall share that screen with you.
Sure.
So let's start from the basic of what is machine learning, what is linear regression and what it is used for. So we should start with an example. Let us consider a bunch of students preparing for their examination. So they spend some time for preparing for their examination. Each student invests some amount of hours. So that is the steady time. Let's take it as a variable. So it goes from 0 hours to not infinity, maybe a student start from 2 weeks before the exam or 6 months before the exam or 1 minute before the exam. So some kind of, let's say, we shall for a typical engineering graduate, it takes just 24 hours before the exam. So we shall have the steady time ranging from 0 to 24. And based on the time they are spending, they score a mark in exams. They consider that as a variable exam score. So it ranges from 0 to 100. 0% to 100%. So we are given these data points as a data set, and when we plot that data points in a coordinate system, it would be like something like this. So let me draw a line. So the x-axis should be the steady time. Steady time. And the y-axis shall be the exam score. Okay. So if you plot the data points in this graph, it would be like something like this. Those who spend less time for studying would have got less marks. Those who study somewhat better get better scores, and those who study a lot would get high mark, and that's good. And that means maybe some outliers. Some might have studied a lot but would have got less score, and some might have studied sometimes and have great scores. So this would be typically the data set would be. So what linear regression actually tries, it tries to find a line that fits these points the best. That's what linear regression actually tries to do. The best in the sense, it tries to find a line that has the least errors. So let's see what is mean by error. Okay, let me draw a function. This is not the best function that fits to these data points, but let me draw. So what the error means is, so this is the actual value and this is what the value we are predicting. So this difference between the predicted value and the actual value is called error, and this is called the error value. So here this value is the error for this x value. So this is the error value. So typically linear regression tries to reduce the error. So how this error is get reduced? Nextly we see like that. So a linear function can be given by the equation y is equal to mx plus c, where m is the steepness of the function line and c is the y coordinate.
What's the technical term for that? Is m called the steepness? What is it called?
Slope.
All right.
It's actually called slope.
And c?
And c is the y coordinate. Y-intercept. When x is 0, the point at which the line is cutting the y, that distance is called y-intercept. Okay. So what actually linear regression tries to,
in machine learning parlance, what is m? What is x?
So actually they are variable weights and bias. That's what actually tries.
Right. Okay. So m is basically called weights in the machine learning world. C is called the bias.
Okay.
All right.
Correct.
Yeah. Go ahead. And
So,
x, would that be a feature?
Yeah, x is the steady time.
Yeah. What is it called? Is it called the feature?
No. That is the attribute.
Okay. Fine. Go ahead.
So y is the future exam score of this. So what we are trying to do is, we first try to minimize the loss. Actually, what the line which we are trying to fit is something. It would be, I'm not sure. Would something like this. This is the best fit, I think so. So this is some kind of line at which the machine linear regression algorithm finds us. So how it arrives at this point? Let's see. So there is some function should be there. By minimizing it, we can arrive at the correct line, the perfect fit line. So how actually minimization is done? Usually by tweaking some values on the input, we are tweaking the output value. So in our case, the slope and y-intercept, by tweaking these two values, we can find the best value for the y, best accurate predicted value for the y for the given x value. So that's our motto. So we have to minimize the error, right? So to minimize the error, we have to derive an error function. So that error function is given by P is equal to 1 by n. Wait a sec, let me explain why there is a 1 by n. And okay, summation.
What are the training samples? You haven't even talked about it.
What we see, what are you actually?
Where are the training samples here?
Actually, that the data set we are already having the data
right.
of.
Okay. So what do you have as inputs?
Actually, I am having the study time and data score as the study time as the input and the exam score as the output. So for the new, for when I have a new exam study time, I can predict some exam score like that. This problem, that's what this problem is.
Okay.
I just problem I got as I am now in exam. So the predicted value of y, which here let me take it as y hat, minus the actual value, that is the y I. Let me take it as this. So, and the squares. Okay. So what it actually says is, wait 1 second again to this. So the error value. So actually we are taking the error value for each points, the predicted value minus the actual value of that point, and we are squaring that value. So this is the error value and squaring. We are squaring because we don't want the positive negative differences. We just want the distance, right? So we are squaring and adding from the 0, it tends from n tends to from 0 to n. So from the 0th point to the nth data point. So we are actually adding those all error values and we are dividing by n. So this is called mean squared error. So technically called. So this error function is called the cost function. In our case, the cost function is least square, mean squared error, mean of the squared error terms. That is called mean squared errors. And this individual terms, this is called the residual. That is the difference between the predicted value and the actual value is called residual, and the square of it is called loss function. I think the terminologies are clear to you.
So what is the difference between cost and loss function?
Thanks for asking. That's a good question. So loss function is the function of the square of the difference for individual data point. So for yi, the loss function would be y minus yi whole square. But cost function is the average of all the loss functions. So that is the cost function.
So can I rephrase like this? Maybe if you're
Yeah.
looking at individual point level, then it is known as loss function. If you're looking for the whole algorithm, then it's a cost function.
So thank you for helping. So next here comes the best part. So how this optimization actually works, how the algorithm finds the line that best fits the points. So
Okay, first question.
Yes.
This equation.
Yeah.
So how many variables are there in this equation?
So actually the predicted value is given by the mx plus c. We will substitute that y value. So we have two variables, different variables. And
I didn't understand. Sorry.
so actually there are two dependent variables in our case, slope m and y-intercept.
So isn't x a variable?
No, x is, oh, sorry. Actually, x is the variable, I think so.
I didn't understand. Sorry.
X is the input variable. We see by predicting by adjusting the value of m and c, we can give the output variable best to y value for the given x value. So
now why is x not a variable in your cost function?
you see, because we are changing the function, we have to tweak the value of m and c. We see, because by tweaking the value of m and c, we can get the best fit of best y value for the given x value. So we are not adjusting the x value, we are adjusting the weights actually. So that's how the gradient, that's how the optimization we are doing the optimization.
Did others understand?
Basically, your question is why m is not a part of our loss function.
No, why x is not part of the loss function?
No, yeah, sorry, why x is not a part of our loss
That's
function.
right. Correct.
But technically it is. Oh, I think you want it from him. Yeah, sure.
No, but what he was trying to say was, I don't need to include. I mean, when you expand this equation,
Yeah.
Abhinav, the
This-
thing is, right, replace your y hat or yi by
Yeah. That's what I'm actually about to say. Wait, let me write it this way.
So better you call it as coefficient and variable so that it will be like
Okay.
spot on.
Collapse.
So are you going to derive this equation for both coefficients m and c?
Oh, the derivative of the two with respect to the M and C, that's what. Yeah, in later part time. So this actually predicted value is given by the function. So function is mx plus c.
no, be very careful there. Is x a variable here?
With respect to x, are we differentiating? That's what you're asking.
No, is x a variable here?
X
Which-
is not a variable.
Okay, so then why do you put an x there? Then it makes it look as though there are three
Okay,
variables here.
Okay, I understand. It's a data point xi.
Yes,
With
that's
xi.
right. Okay.
So xi plus the actual y value. Y.
No, minus.
Oh, sorry.
What's n?
So n is the number of data points. So from zero data point to the n.
Come up with a better nomenclature. Wouldn't that be I? I is equal to 1 to n, right?
Okay. Yeah.
Make it I 1 to n.
Thank you. So it's okay, correctly.
All right, that's correct, but I want others to understand. So here, xi and yi are data points. So if you look at this graph, these are data points that have been given to us. So there are a lot of data points that are available. So in this equation, when you apply this equation, xi and yi is not a variable. It doesn't change. It's part of the data set. So don't get an impression that that's a variable too. So the question is, from an equation standpoint, what is a variable? Is n a variable? Let me ask this question. I want somebody to answer. Is n a variable here? I've given you a data set comprising of, say, 40 data points, and Abhinav has plotted it. So you have xi, yi. When I use the term xi, yi, it's a data point, by the way. All right. So my question is n a variable in this equation?
N is from 1 to 40.
No, n is 40.
Yeah, 40.
Right? So n is fixed, xi is fixed, yi is also fixed, right? So xi and yi essentially runs from 1 to 40 if there are 40 data points. So if you look at this equation, it's basically an xi, you'll plug in a number xi, you'll plug in a number yi, right? And of course, m and c certainly are variables because you don't know what values you're supposed to plug in against m and c. So it's basically a two variable equation that you're squaring, right? Okay, sorry, Abhinav, go ahead.
Okay, next comes the optimization part. So we have to minimize the error function. We have to find a line which has the minimize the error value. So that's the line we have to find. So minimization, in the sense, you would all be saying, let's put the first derivative to 0, or in the multi-dimensional, put the gradient equal to 0 and solve the equation. Okay, you can, and that's called direct method.
It's technically called the closed form solution. So let me explain that a little bit. So you want to reduce this to 0. So let's go back to our own, the old class 12 calculus, you have a function, a simple function f of x is equal to, just plug in a function, Abhinav. F of x is equal to x square minus 5, let's say. And you want to calculate, say the maxima or minima. What would we do? Go back to class 11, 12 calculus. You take the first derivative of x square minus
so we'll
5
check. Yeah,
equated to 0.
yes.
And then you figure out the value of x, right? Now that's what is called as a closed form solution. Now, that's for one variable. You can do something similar if you have multivariables as well. So in the multivariate world, where if you have, say, f of x comma y, there are two variables, let's say, right? So what we do is, instead of calculating, instead of differentiating it, you calculate what is called as a partial differential. So dou of the function by dou x, dou of the function by dou y, right? Equated to 0, and try to solve, right? Again, class 12 calculus. Now, if you look at this equation here, the error equation, it's an equation in two variables, m and c, right? So to get the closed form solution, all that you have to do is take the derivative of the error, the partial derivative of the error with respect to m equated to 0, take the partial derivative of the error with respect to c equated to 0, and try to solve. And whatever value of course, there is a second derivative that you need to take to figure out whether it's a maxima or a minima. I don't want to get into all that. All right.
I'm about to tell that.
Yeah. That's there. But I don't want to complicate things too much. But that's the basic principle, that you take a simple derivative, a partial derivative, in fact, equated to 0, and then figure out what should be, in this particular case, m and c. And that is called as a closed form solution, right? Sorry, go ahead. Naveen,
Sorry,
yeah, go ahead.
No, I was telling, if you can tell what the definition of convex function is. Like some people may think, right? So if it is a convex function, what if it has a local minima? What if it has a multiple local minima? Where that
I think he'll come to that. You have something to say about it, Abhinav?
Yeah, SVC, what is the problem with this closed form solution?
Okay.
Yeah, he'll come to that. He'll come to that. Go ahead.
Oh, yes. So actually, so we can say, why can't we are arriving at this, arriving at the precise solution, we are finding the minimum point easily by this method. So why do we go for gradient descent? You all will be asking. So, but the problem with this is two-dimensional thing, so that we can easily find out the gradient and equate it to 0. But when we do with lot of variables, so at that time it is a bit complex for the machine to process. It is computationally inefficient. So that's one case. And the second reason why it is not widely used is this method is used only for few of the algorithm which we will be learning even in this course. Only a few models can be solved by using this linear closed form solution method. So for these things, we are going for the gradient descent. Have we covered all this?
Go ahead. Do you have a presentation? What else are you going to share?
Actually, I was about to make this calculation manually and explain them with the presentation. So
go ahead. What do you have? Don't get into a lot of details, but because the objective here is not to.
Yeah. Actually, I want just to explain the gradient descent.
Yeah. Go ahead. Yeah.
So, okay, now what gradient descent actually does? So gradient descent, let me draw a diagram first. So this is my error function. And this is my weights. So for example, let me take the slope.
Yeah, Abhinav, I have a question on the linear regression. Sorry.
Yes.
So the error function assumes that, or the cost function, right? If that's the sum
Yeah.
of the errors,
Yeah,
that
yeah.
assumes that you give the same amount of weightage to each of them, right? Is that correct?
What I think as Joseph.
Yeah, you're right, Jose. You're right. So basically, what we're doing is the weightage assigned to each loss,
Yeah.
right, is the same.
Yeah,
So
same.
it's right.
Yeah, is there a way or within this algorithm, right? If we know that there are certain data points that has to be given higher importance to, is there a way that we could work within the linear regression model to define that?
So you're trained for for the outliers, we can give the importance, less importance. So like
Yeah,
that.
exactly. Yeah.
Not in linear regression. I can't think of.
I'll answer this. So people have tried doing something like this, but this is not a very generally accepted practice. We'll once we finish linear and logistic regression, we'll go into tree-based models, where this is more common, or this is more acceptable practice on how to provide different weights for different observations. So that's something that we can do, but we'll come to it later. Let's first understand the basic flow, but great question. Yes, it happens, but it happens only when you have such deep understanding of the domain and the row that you can go and do. I'll also give an example of where this would happen. We remember we did this entire example around loan default models where it's extremely imbalanced. It's not too imbalanced, but 10% of the defaults were only 10% of the entire sample that we had. I want to ensure that when I predict something would default, I want, and you can pick a metric. We haven't defined what precision in recaller, but we'll come to it later. But let's assume that I want a highly precise model. So which means that I would go and then weight every single default that's out there with a higher factor compared to a non-default. So which means that, or say for example, here I want to have a recall to be close to 100%. So I would weight it by a very high factor, so ensuring that everything gets handled in the output function. This is generally not a problem in a linear model, because a linear model in general is unbounded. It's minus infinity to plus infinity is the domain on which the output is operating. And when you have something like this, having the necessity to influence correctness only for certain rows is not a general use case. So not something that's taken up. Does it make sense?
Yeah. Thank you.
Yeah, continue.
So let us consider the graph between the error function and the slope. So it is typically something like this, I'm assuming. So okay.
Is this how an error function would look for linear regression?
Yeah, yes, we see some. Actually, this is some higher dimension. I was just trying to explain how it works.
Okay, so this is not specific to linear regression, right?
Not specifically.
Okay.
So this is something like this. I think. So okay. So for that, first we have to learn what is gradient vector. So for a given function, gradient vector is a vector which gives us the direction of the maximum of the rate at which the function grows rapidly. For example, at this point, if we take the gradient vector, it will show a point us in this direction. So let me use some color. So So this is the direction of the gradient vector. So what gradient descent actually we are doing is, at each, we are taking the gradient at each point and we are moving in the direction opposite to the gradient. At periodically we are updating our weights, our slope and the coefficient and y-intercept. So the point is initially randomly assigned at anywhere in the function. It can here, it can be here. So in gradient descent, we can achieve the local minima. Finding the global minima is not possible. So what we do is, for example, if we are,
Why do you say finding the global minima is not possible?
so wait. So
I can
point-
start at this point. Okay, help me in 3-4 steps. Take that point there, the point on top,
okay,
one to the left, the one to the left.
this point.
No, the one to the left of that. Yeah.
Yeah,
Take
yeah.
me through the steps. So the first step is how will correct. You'll start that way. Correct. Then next step, you go down. All right. Then, all right. Then, yeah, keep doing that. All right. And then at that point, what happens?
Okay, that at that point it converges.
All right. That's fine. But how will the gradient, how will the vector look?
So it looks something like this. I'm not sure.
Is that so? Then I'll continue, right?
No, you see, actually, what we are having the criteria that when we reach the minimum point, at that point,
How do I know that
gradient-
how do I know it's the minimum?
Yeah, we are taking the gradient vector.
That's right. So
Yeah.
what we've done so far is, if you look at that point, that particular point that we were looking at, the minimum,
Okay, okay.
the minimum,
Yeah.
don't you see that? Look at that arrow, always when you draw a vector, the arrow, I mean, the length of the vector determines the magnitude, right?
Yeah.
So don't you see that?
So actually, we are not reached the accurate value, but we tend to reach, if I'm not wrong. Am I right?
Think about it. It's the slope, isn't it? The
Yeah,
gradient is a
Yeah,
slope.
vector.
So what's the slope at that point?
At that point, slope is 0.
Correct. So what is the length of that vector at that point?
0 vector.
Exactly. Right. So
So
imagine, so the two parts to it. One is direction, of course, that we understand. So we are going down that curve, but there is the vector has a length as well, and that's basically the slope.
Yeah.
So at that point, at that minima, this again goes back to class 11, class 12 calculus, folks. When you draw your function, when you figure out the maxima and minima, what you would find it is at maxima and at minima, the slope would be 0, right? That's precisely what is happening here. So you keep going down, and at that point, you'll find that the slope is 0 and you stop because you don't want to move, because you kind of reached what is called as a minima. But the trouble is, let us say hypothetically, instead of starting at this point, Abhinav had started at a point on the other side. Not this one. This one, the one to the right of that. No.
That one.
That's right. Now you keep coming down, Abhinav. Keep coming down. Yeah. You keep coming down. Make the line look a little smaller because the slopes are slowly decreasing, right?
Yeah.
At each step, the slope will, the magnitude of the slope will keep decreasing. And then at that point, it's 0. The slope is 0, right? Now, okay, this is not a fantastic graph, but if you look at it, this minima is certainly not the global minima.
Yeah.
The global minima is on the other side, right? So one thing about gradient descent is, it's possible that, it depends on, when you have a function like this, you might end up reaching what is called as not a global minima, a local minima, depending on where you start, right? So if you were lucky enough and if you started at the point where we started initially, then you'd have reach the global minima, but then had you started at the other point, you'd have reached what is called as a local minima. Now, just one point there. Abhinav, can you draw a convex function, a typical convex function? A convex function. Yeah, exactly. Right. Now, when you have a convex function like this, it doesn't matter where you start. Abhinav, take a point to the left, keep coming down. Keep coming down. Yep. Draw a bunch of vectors. Yeah, keep coming down. Like that, like that. Yeah, good. Eventually, just make it a little smaller so that people understand that the size of the vector will keep decreasing depending on the slope. And finally reach that point, yeah, where the slope is 0. Now that's the minima if you start there. Now try doing it on the other side. You just pick some point closer. You don't need to draw so many vectors. Yeah, maybe let's say you started here. Yeah. Keep coming down, keep coming down. And finally you reach that point where it's again 0, right? So when you have a function like this, a convex function, it doesn't matter where you start. You can reach a global minima, which also turns out to be a local minima, right? And Abhinav, correct me if I'm wrong. For linear regression, the functions are convex functions. Is that right?
Yeah. Yes.
It's a convex function, right? Okay, sorry. So go ahead now. Whatever you wish to say.
So let me present my presentation. We see that how this derivation.
Abhinav, one question before that. How do you
Yeah.
know the slope is 0 here? How do you compute it? And like when
Yeah, actually, that is also in that slide. When we are deriving a function, the gradient vector only we include in the formula. But when the gradient vector is 0, so there is no weights don't update anymore. Am I right?
So it's based on your, like every time when you train your learning rate and when you take your first derivative, as the slope decreases, the value of the first derivative also diminishes. So
Yeah.
how much ever epoch you run, still the vector will be at the global minima.
So
Like
at one time it converges, right?
Yeah, so it is based on you, right? You can keep some metrics
Yeah,
telling that,
yeah.
okay, I won't train more than this many epochs, or I won't train more than, let's say, R value, R square is same for last 100 epochs.
Correct.
That's your way of stopping
That's
it, but
our
there is no like proper way telling that, okay, if it's this, I should stop it. There is no way like that.
Yeah, at one time it converges and we shall stop at that point.
Yeah, how do you know how it converges, right? So yeah, go ahead.
Actually, when we get the first derivative of, shall I share my presentation?
Yeah.
Or no?
We see I have a question.
Mm-hmm.
So in that particular graph where we are actually plotting E versus M, right? Okay. Where we
By the way, that's not a E versus M is not the right graph that we should be drawing here. We should be drawing a
so that's the first question.
E versus M and C. So it's actually a spheric. I mean, it's a 3-dimensional surface that we should be drawing.
Yeah.
Okay. So that's one question. Okay, so that is clear. That's what I thought. It should be like that. So we are actually calculating with two different values, means different values for M and C, and we are actually plotting that.
That's right. Do we have a?
Okay.
Abhinav, by any freak chance, do you have a surface like that? In your presentation? A surface. Do you have a surface?
So is the nearby any surface?
No. In your presentation.
Yes, I think.
Can you go to the presentation? Let's switch to the presentation now.
So one more thing, one more question is like, say now you said, let's assume that N is equal to 40, right? Means like we have that number of data points, we have it as 40. So now to do this particular E versus M and C, right? So I will, how many M and C I will actually take? That is actually,
M and C, no, see, and okay, I have 40 data points, correct?
40 data points. So
M is one value that I'm trying to figure out. C is one value that I'm trying to figure out.
Correct.
right?
Okay.
Now I have an equation now. It's actually it'll be quadratic in nature in this case, right?
Okay. So in this case, it is y is equal to mx plus c. Correct. So that's the equation we are actually starting with.
That's right. Correct.
So that's the equation. So now we'll have to find error for different values of m and c, and then whichever is the minimal one, that is what I'm going to take.
That is right. Correct. That's one way to look at it. Correct. Yes. Yes.
Correct.
Certainly.
So now I'll start with some m and then see like what is the value. I'll actually increment the m value, increment or decrement the m value and c value, and then I'll slowly do it out.
That's the algorithm doesn't work like that. The algorithm works a little differently, but in principle, you got it right.
Okay. So that's what you wanted to do.
So what the algorithm does is you have that cost function, and the whole objective is to figure out a value of m and c such that we get to the lowest point, right? To minimize it. And the way to do that is to calculate a derivative, the slope that we talked about, and keep moving down that. What we saw was line, but effectively what we'll do is we'll move down a curve. I'm sorry, a surface. And then come to the lowest point in that surface. Whatever is the m and c that will allow us to reach that lowest point is the number that we're looking for.
Okay.
Right?
Got it.
But if we see this graph, right? I mean, weight is referring to M or C?
For all practical purposes, interpret both m and c as weights.
Okay.
So we have two
are
weights. Imagine two weights here. That's I mean, technically it's a bias. C is called as a bias, but let's not grapple with such terminology. You can, for all practical purposes, you can call both m and c as weights. So you have two weights that you're looking to optimize, right? You're trying to figure out what is the best combination of these two weights that will result in a minimal error. Exactly. So this is called as Abhinav, do you have the weight space with you?
Yes.
Okay, show us a transition between data space and weight space.
Okay.
So can we assume that this diagram which is there, right? The convex function, that is basically error function or the cost function which we are trying to minimize.
That's right, correct. So if you look at this, what you see to the left is a data space, okay, where there is a y of course in the y-axis, and there is an x in the x-axis. You have a line associated with each line. With each line is a m and a c in our world, right? Correct? Would you agree? You take a line there. Let's say one line is the best fit. You don't know which one. Let's pick this red line, for instance. Don't you see it's a straight line? So which means there'll be an m and a c, right? M will have some value, c will have some value, correct? Now, again, we don't use m and c in the machine learning world. We just call them weights, right? So you have two weights here. Now, what you see to the right is a representation of the line in the weight space. So I said there are two weights, right? Correct? So the y-axis, you plot one weight. It could be m in our world. In the x-axis, you can plot the other weight, which is c in our world. And then for a combination of weights, you'll have an error. Would you agree? It's not visible here, which is why it's three-dimensional. For a combination of weights, basically for a combination of m and c, you'll have an error, right? So if we look at the three-dimensional surface, what you will see in the three-dimensional surface is you will see weights, in this case, two weights. And then do you have that?
From Google.
Please show that. Please show that so that people can visualize how it will look in three-dimensional space.
Something kind of this.
Exactly. But you need an axis. Okay, just imagine there is a, okay, this of course, imagine, Okay, we need an axis here. Now this won't work, Abhinav. Okay, this is somewhat okay. This is somewhat okay. So there is an x-axis, there's a y-axis, there's a z-axis. Imagine the z-axis to have the error, or what you call as a cost function. And then x-axis is one weight, y-axis is another weight. So what we're trying to do is, we are trying to find the value of x and y such that the error function is minimized, which is literally at the bottom part of the surface that you get to see, at the most, I'm just saying the bottom part, but you go all the way down and you identify the point where the error is minimum and identify the value of the weights. And that's your most optimized value. And you use gradient descent to do that, right? So as Abhinav said, for linear regression, there is a closed form solution. You could have calculated it without doing gradient descent, but most algorithms will not have closed form solutions like linear regression. Most algorithms don't. And we always use gradient descent. Not always. Most of the situations we would end up using gradient descent to figure out the minima. So, of course, then why did we pick up linear regression as an example? We picked up linear regression just to demonstrate that, look, it's easier to demonstrate. Many people can relate to linear regression as compared to any other algorithm, any other model, which is why we picked up linear regression. Abhinav, just quickly go through the algorithm. Let's not take a lot of time. I think one thing that is important is get the intuition right. That's very, very important. We may not get the, it's not necessary that you get the details right away, but get the intuition right. That's important more than anything else. And most importantly, get the formulation correct, in the sense you should understand how we are formulating the problem. If you're not able to understand how the whole problem is formulated, then yes, it's problematic. But if you're able to understand how the problem is formulated and then the intuition behind the algorithm, I think you're good enough.
One last question. Always the cost function will be convex only, like this?
No.
How do you ensure that it is minima?
In this case, for linear regression, it is. Right?
What if it is concave? We end up with
okay,
maximum,
that's
right?
I think I'll leave it to Bhargav. Much more experience with all this. Bhargav.
I'm so sorry, I missed the question. Can you come again?
No, the question was, for linear regression, the surface is convex, so you can go all the way down and grab the minima. But Shirisha was asking, what if the surface were to be a concave surface?
We talked about it, right? The cost function has to be convex. So that's one of the definitions on how a cost function has to look like.
So cost function is always convex.
Yeah. For now, just assume that cost function is always convex. Yes.
Okay.
If you don't have convex function, you will never be able to converge. You'll always be stuck in, like the diagram that Abhinav showing his screen?
Yeah, he is. Can you go to the diagram, the other one?
The diagram that you showed.
The crazy curve that you had.
The one that you had, E versus M. Can you show the E versus M diagram? Because that, like before I could tell that it will never look like that VC jumped to it, but it's so obvious when you see it that an error function plot would never look like that.
Where did it go?
It was on your Excali draw somewhere. Like this, right? This one would never be like this, because you see that the so this is not a convex function, right? A convex function is like how it's on the right. So if you're in this, like now, you'll be stuck in what is called a local minima or a local minima. It's not something that you want to get in. So you want a cost function that's convex, so that there is one global minima that you can work on ensuring that you reach. Now, the challenge is, Abhinav made a very fascinating point that some of the times these cost functions can be so complex that it's even computationally intractable to figure out how the convexity looks like, because it's in so many dimensions. At that time, you might be so unlucky to enter a particular surface which will look like this. But that's all something that we'll leave to when we're dealing with a lot more weights. When we come to deep learning, we'll think about it and see how some of the newer computational techniques that how would you go about doing, say, a gradient descent to do it. But this one point that Abhinav made, I have to correct it. Doesn't matter what algorithm that you do in machine learning, what you're learning today is the fundamental thing. There is one cost function. The cost function has to be convex, and the learning is through gradient descent. So these are true things that doesn't change. What as of today, based on what the state of art is, the learning is through gradient descent, and the cost function has to be convex. We'll think about adding some complexities to the cost function very soon, maybe later today or tomorrow. But always remember that it'll be convex and gradient descent.
Gradient descent meaning reducing, taking one point and reducing that value to find the minima, right?
Yeah, we discussed this in last session. So always remember dy by dx has to 0 is the approach that you would take to find minima, right? So that's what we are trying to do. Instead of doing it all the way in, because like continuous functions computation is quite complex in computer, we would use, and I mean, it needs to be done partial derivative for every single weight. We would do something like, who's writing this?
This is Abhinav.
Abhinav is writing, where we're just going to move slightly in the direction of the gradient itself. So dou E over dou M is the partial derivative with respect to the weight M, and then we're going to make an adjustment to the value of M in the direction of the gradient.
It's opposite direction, right?
Opposite.
Yeah.
In the direction. You're going in the direction of the gradient.
Is that so?
Making
Okay.
an adjustment in the direction. If you make an adjustment in the direction of the gradient, you are reducing. If you go opposite, then you go up, no?
But gradient goes up, right?
Gradient is the maximum rate at which the function increases. Gradient vector gives that first to us.
Gradient always defines it increases.
Gradient is the slope, no?
It's a slope. Gradient is a slope. So in this particular case, I mean, what would the gradient be? It will be a negative value, right? Correct? In this case?
Correct.
Yeah.
Right. So in that case, you would still go along the gradient in this case, isn't it? Right?
Correct.
No? Because if you flip the signs, then you'll be moving in the opposite direction, wouldn't you?
In the opposite direction, correct.
Correct.
Right?
Yep.
Yeah,
go ahead. So what's alpha, by the way?
So alpha is the step size or learning rate. So for instance, if we have moved here at this step. So based on the step learning rate, the movement towards the minima happens. For instance, if the learning rate is too high, the function may not even get to recognize the minima. Wait, I'm drawing something new. Let me draw something new. So let this be the function. Okay. So if the learning rate is very low, it takes a long time. So it moves very small steps. If the learning rate is very high, it may overshoot. It takes a long steps. Okay, it may not even find the minima and it diverges. So the problem is we have to choose the correct learning rate for our problem. So an optimum learning rate is very important in gradient descent. That's a hyperparameter even.
Okay.
Also, two things to add here. So the first part is gradient may not always diverge to 0, which is computationally too heavy. let's say if you're running 100 epochs, it's unlikely to, like, not all the case, at least for the simple equation what we are taking. So it's very hard for it to converge. It will be somewhere around 0.0111. So it may not be always zero. If you want to achieve zero, I don't know whether it is possible computationally or not, because it's like a huge number. So two things where you can stop. So one is you can define a epoch telling that, okay, I'll run it 100 times and I'll leave it. Or else what I can tell is I'll run 100 times, I'll run for infinite times. And let's say if for last 100 times while I'm running, if my metrics, whatever the metrics can be, doesn't improve, I can stop it. So these are the, okay, this is one thing. And other thing I forgot. Okay.
It's okay. Just a brief overview. Abhinav, just give us the brief overview of the algorithm so that we understand.
So actually, from the start,
No.
Let gradient descent.
I'm so sorry.
Sorry, go ahead. Yeah.
Like LBC, I'm not sure whether Abhinav mentioned it. Like, how do the vector get diminished? Like, did he cover the part? Because the error will get diminished, right? So whenever you do this thing, like, is that?
No, I don't think he covered it. At least the way you suggested, he didn't do it that way.
Okay.
I think what he said was the slope would decrease. So because the gradient is a slope, so as you keep going down and as you go closer to the minima, dou E by dou M would keep decreasing.
That term diminishes.
It keeps diminishing, right? So that's what he said.
Whenever you do a derivative of your cost function, what do you have? Like for the at start, the difference will be huge. Let's say because your actual variable will be somewhere, your predicted variable will be somewhere. Whenever you're optimizing for the best solution, dou E by dou M will get reduced by like it will get diminished close to zero. That 0 is our optimal solution. It may get diminished close to 0. So that is where when you stop it. So that is why you see, right? So first step will be longer, next step will be shorter. The next step will be even shorter. So that is the reason of the length or the step size.
So Abhinav, just take us through in brief the algorithm. I think you have something on your presentation, right? Don't you?
Yes.
Yeah. So Naveen, whatever you said, Arun here. So whatever you said, the first step will be longer means what? The alpha will be changing.
Not alpha. The dou E by dou M
E by dou X will
be huge.
Okay.
It's imagine that to be the slope, Arun. So don't you see that the slope will be high initially, and then as you come closer to the minima, the slope will come to 0, isn't it?
Okay.
Actually, this is how the gradient descent work.
No, we're not able to see anything at the moment.
Sorry. Screen sharing is paused.
Yeah.
So now are you able to see this?
Yep.
Yeah.
The last slide. Okay. So first we have to pick a random value for the parameter, as I said. Then we would have calculated the gradient value at that instance.
Sorry. So when you say parameter, what is this parameter?
The slope. The slope.
Is it so?
Each parameter.
M and C are the parameters.
M and C. All right. The weights, right?
Yes.
Okay. All right.
So then substitute the value in the derivative. Actually, we are updating the parameters. Then the new parameter is updated regularly for each epoch. So at some point, the value converges, and that's where we stop.
So we've been using this term epoch. So in this context, what is epoch?
Epoch is for example, if we run a loop, the number of iterations it runs.
Okay, so let's say I have 40 data points. If I move from one data point to another, is that an epoch?
I think it's not.
Okay, so what is an epoch? So let's say I have 40 data points with me in my data set. And then, of course, I'm doing linear regression and I'm trying to figure out the minima using gradient descent. So what exactly is an epoch?
So, for instance, if epoch is the number of times that algorithm runs, for example, once you calculated the Okay, let me explain in this context. There is a value of the slope. Then for one while, we are calculating the gradient at that instance. So we are updating the parameter. So then the new slope value arrives. So this is one epoch. So like that, it happens.
Okay, just sorry, one moment. Bhargav has said, I mean, he conveyed that epoch as a concept is not particularly applicable to linear regression. Why is that so, Bhargav?
Even I'm curious.
Yeah, you guys are. This is called what? Word overloading, right? Word overloading right now. Because
interpreting it philosophically, to us it looked
no,
like an
it's not
epoch.
about interpreting. It's because Abhinav has already read some lectures on deep learning. He's trying to force fit his knowledge into linear regression. Unfortunately, that's not how it works, right? So his explanation is correct, but not in this context. So for you to know this, Abhinav, okay? So in traditional machine learning models, which is what we're going to cover this week, next week, where we talk about linear regression, logistic regression, and then when we get into tree-based models, decision tree, random forest, gradient boosting models, it always works only by taking the entire data into account. Your gradient, when you compute, is computed across the entire data points. Okay. So it means that the it puts a cap on how much data point that you can have. So it's dependent on the RAM that you can load into your memory. So if the entire data can fit into a memory, then your model will be able to build and converge.
Bhargav, question.
So,
aren't there some exceptions to that, such as stochastic gradient descent?
Correct. Stochastic gradient descent is the solution to solve this problem, which is how neural networks learn.
Okay,
right?
all right.
A stochastic gradient. Okay, that's why I'm
no, let's not get into that. Okay,
like
for some other day.
That's the reason. So concept of epoch comes, which is the explanation that Abhinav gave. So he understands, like now I understand that he understands stochastic gradient descent really well, but gradient descent is decided on the entire data set. Stochastic gradient descent happens when you have only, I can't load my entire data into my memory. So I need to load my first 10 data points, my next 10 data points, my next data points, and then I load my 100 data points, like the last is 10. That when I finish loading all of my data points and train it, it's called one epoch, right? Let's introduce this more formally and in a way that everyone can understand later on. But now remember that if you have 100,000 data points, you're going to load 100,000 data points, your entire data set into memory. And then on the entire, and then for every one of it, you're going to find what the error is. And then the gradient is computed across your entire set of rows. And because you can do that, we will be able to solve the question that Joe's asked, is that can I weight a specific row? Because I'm going to learn across all of it. The algorithms allow you to do weighted regression, weighted classification, which will come back, which we'll learn a bit probably next week, right? So that's definitely possible. So gradient descent works by loading entire data into memory and computing gradient on the entire data set. That's something that you need to know. The fundamental difference as you move from machine learning models to deep learning models, and why deep learning models are the way to go and solve as you have tremendous amount of data, is for this concept of stochastic gradient descent, which we will talk about later on. Because how will you break the data, how will you learn, and how do you update the weights, and because you're going to have more weights compared to the data set that you have, there's going to be a whole bunch of complexities that you're going to introduce. So we'll talk about all of it when we get into the formal theory of neural networks.
Thank you.
Is anyone having any confusion on this? Because this is important to know. Abhinav, are you clear on this?
Yes, fine.
So when you don't do it on a certain set of a batch of data. You're taking on the entire set of data. That's one major difference as you move from these kinds of models to deep learning based models.
All right, we'll just stop here for any further questions. Strong recommendation, please read it up. Just having a look at this presentation may not be sufficient. Any questions so far?
So a small correction is required, right, in this slide which Abhinav is sharing for each parameter.
The slide is correct.
Slide is correct.
has
Okay.
no problem.
It's just that the loss function would be determined for, you'll take all the data points and determine the loss function. That's what
Oh.
Bhargav is trying to hint. You will not determine it for one data point and then calculate the gradient. You'll take everything put together and then you'll calculate, which is why you have that sigma, right?
Sigma. Yeah.
So you do it for the entire set of data points and then you calculate the derivative.
Yeah, that is what is cost function. Individually, it is called loss, right?
Loss function. Yeah, I didn't know the terminology. I mean,
Yeah.
it's the first time I'm hearing. Okay. Looks like.
We see the
Which
fourth.
terminology we see?
Loss function, cost function.
They're the same. Loss function and cost function are the same.
Oh, okay. All right.
Used interchangeably. but
Okay.
Loss is for, like, cost is for the whole. Okay, then okay. In deep learning, it comes to an
It's the
epoch.
same
level.
function. You can call it cost function also. It's just
Okay.
a terminology. They mean the same thing.
Interchangeable, is it? Lost and cost.
Yeah, loss and cost function are the
The
same.
cost
Okay.
will be the summarization of the loss, right?
Like, given any set of data I want to compute my loss, what's the cost? It's the same. Right? Anytime learning happens on the cost function, right? It's just an interchangeable terminology. It depends on which grad school they went to, like what terminologies they use. Is all like, that's pretty much it. They mean
Alright.
exactly the same thing.
All right.
Uh,
Sorry,
two
Arun.
questions. Yeah, two questions. So now we are in the step number 4. We are saying step size is equal to slope into the learning rate.
Correct.
The slope is like, so now I'm actually doing my first iteration, and I have a function for that. I means like I identified the MNC for that. With this MNC, I'll actually calculate the particular slope that I'll actually use it here.
That's
So
right. Correct.
that's where Naveen said is like from each of the things, the slope you will be able to get you are not actually going to do the learning by step, the same learning rate, but the learning rate is also going to be faster, and then we'll do it. Is it right?
Learning rate, generally, do we change it, Bhargav? Usually we don't, right? It's a
No,
hyperparameter, right?
No, I'm saying learning rate is not changed, but step size is changing.
Ah, correct. Yes,
So-
because
so-
the
so-
slope will get smaller, right?
Yeah,
As you
yeah.
keep.
Yeah.
Actually, we can even optimize the learning rate. For each step, we can change the learning rate. There is something.
Yeah, you can, of
I
course.
think let's not pick this up for this.
Exactly. May not be
Yeah.
very suitable here.
You're
Yeah.
introducing concepts which are not relevant for these algorithms. I'm just telling
Yeah.
you, this is another mistake that you're making. Again, this particular concept you told is not applicable when you have the entire data and do it.
Okay.
Okay. We'll talk about having a learning rate schedule when we do deep learning. There, it's a very important concept to have a learning rate scheduler. And in
Linear regression.
it's not linear regression, logistic regression. You wouldn't have a learning rate scheduler. No, it's generally fixed. If you need to write variable rate, then you need to go and do it. Out of the box, no algorithm provides it. No library provides it.
All right. Thank you. Vidya, you had some update on Idli Vada Dosa, right? Yeah.
Yeah. No, that was GradCam visualization. That yeah, let me share the screen. I'll share the results for now.
So what is GradCam visualization, Vidya?
Yeah, actually, that is like a gradient class activation map. That is an the full form of it, and it actually helps to visualize like how on what basis this image was classified as an Italy, or on what basis did it classify? What are the weightages it took to understand this is this belongs to this category? So that's what I understood for now. And so this is actually what happened here was we actually used the trained model, and then over that we used the GradCam visualization, and we did this original image, which is can you see this original image? Yeah. And then the prediction was it says Italy. So what I understand from this image is that we can see there are blue, yellow, orange spots here, right, around this area. So the red ones are actually like the blue ones are, correct me if I'm wrong, Bhargav, here. The blue ones have very less weightage.
No,
Spot,
blue
like
one has
blue-
the greatest weightage.
Yeah, less weightage, right?
A blue one has the greatest weightage. That is where the model is focused on.
All right. Then this makes sense. So the red ones are not the hot spots. Like it's so the blue one and the orange one are the hot spots, right? Like for predicting that image. So this makes sense. So here we can see that the blue ones are concentrated on this this piece as of like you can see that Italy has been highlighted into blue. So that's the reason why this this model has predicted that this particular image is in Italy here. And then over here also it has predicted for all these three combination of the categories we have predicted it's Italy, because the blue ones is what have high weightage here. And then here is another visual test image that we used, and this one is like as you can see, the other area, the red areas are being have been given a very less importance, and only the blue area and the yellow ones are being considered has been considered as a heavy weightage to consider this image as a dosa image. And
So,
here and
I'm so sorry.
yeah.
Finish it. I'm so
Yeah.
sorry. Finish it.
And here, I think this one makes, I was not able to understand why this part here has been given as an heavy weightage for considering, this one is just like the sides that comes with it. And I could see that the blue regions have been, has been concentrated around this area. So.
That's a part of your error.
That's a part of?
Your error, right?
So right.
Oh, you have
Maybe
80% accuracy then.
right. So I have one question here. If we are going to use more images, say like if we are going up to 10,000 images, then will this error be reduced? So that's the reason why.
No, okay, it's like the orientation of image, right? Let's say you have only one white plate, you have 20 images of those and 20 images of idli. All your test data is going to be on the same white plate where the folding is same, the position is same. Then 20 data is more than enough. It's all about the distribution of data, different backgrounds, different things, right? So it does really matter.
Right. So.
And one curious question, like which layer have you applied this GradCam?
Yeah, it's in the last layer. Let me
last layer,
the target layer. Yeah, the target layer was let me share. So
you have it in GitHub, right? I'll check.
What is that, Navin?
You have this in GitHub, right?
No, I haven't shared it in GitHub yet. Like let me just share it now in a few minutes.
Yeah.
So yeah, I'll you can see my code now?
No, still the Word document.
Oh, right. Just a second, then I'll share it.
I just want to get a sense, everyone else following what Vidya is showing?
I wanted to ask, how does it distribute the weights? Like, how does it, how does it weigh out the image? What goes behind it?
Yeah, I'm still learning on that. But what I understand from this is, you see the blue spot over here, right? The blue, you can see blue, yellow, orange, and the red. So as Navin said, the blue spots have been given a high weightage of predicting this image as as in this category as Dosai, and the red spots has been given like very less less weightage for predicting this image. So mainly it is based on this blue spot. It is just based on this blue spot. It has predicted its Dosai, and not considering any other spots.
Actually,
around the image.
it is the pattern that is recognized by the layers. Am I right?
Yeah, I guess so. So, but what we can see here is, even though we had, we can see this area like it's been given, it's similar to this one, right? So this image over here, this original image and this one is kind of similar, but still it has given weightage to this area only, the Italy area only, because that may be because we had more of the training data which had Italy in the plates near to the sites. So that's the reason I predicted Italy. So I'm still I'm not sure how on what basis this happened.
Wow.
I
So
think
this one
we are
is quite
trying
Abhinav.
with having the three nodes so that it might collapse if I'm not wrong. So if we individually
Actually, we didn't use these two images for training purpose at all. I just trained it only with plain, the images which had only Itlis and which had only dosas. So these images were not as a part of training set or the test set. This one I just used for,
So was most of your image, was it Idli? I mean, just wondering.
No, I actually had it equal amounts. So I don't want to make that, I just wanted to see if I give equal number of images in each category, how it predicts. But I was like, I'm not sure why it predicted, this instead of dosa, because I see it's in the middle of the, I was expecting this image to be predicted as dosa, but it has been predicted as Italy. So maybe because we didn't have lot of images that had dosa on white plate. Instead, we had Italy and sites as in the white plate. So that's the reason why it went for Italy and not for dosa. I'm not sure.
But
Maybe.
okay, maybe we should try giving. I mean, if we can find images where you have dosas on a white plate, and then
So we
train it,
have
and
to
let's
give,
see.
and again give this image to
Yeah,
it,
let's
so
see
it
how
will
it
predict
goes.
dosa only instead of Italy. So
We'll have to see how it goes. Very
yeah.
nice. Thank you.
So this is yeah, I'll share the code on GitHub now. So this is from
do you
my
understand how GradCam works?
me.
No, Naveen.
Yeah.
Bhargav, not to the extent that. So what the thing is, right, for like the weights is not going to change for each and every image. The weights will be the same. So whenever you get the input image, it gets multiplied, and the one like when you I do think so. The one which has the more number of weights, the pixel which it has the more number of weights, I think it will come out here. I haven't studied how this works.
So Naveen, what do you mean by more weights in this case? So you say that a blue area has been given more weightage?
Yeah.
I understand that blue area has been given high weightage here, but is this based on the training data set that's been provided?
Yes.
Yeah.
So maybe next session I'll do a read up and welcome. I've used this n number of times, but we used it as a check whether the model will work. We didn't think
Stop sharing the screen now.
Yeah, sure. Someone's partying now. Okay. So this is a question for everyone. We saw, I mean, this is an example of where we are building a classifier And there were two interesting elements in what Vidya shared. One is that she built only on idli and only on dosa. And suddenly when idli and dosa were in the same image, it didn't work, right? But this is a common problem that we would also face. Anyone has any idea how, except Naveen, anyone has any idea how to solve this problem?
So you mean by giving that how to predict that three combination data?
Now
Okay.
at that point in time, I can have anything. No, I can have vada, I can have chutney, I can have sambar.
Yeah. So we have to provide a weight. We have to define a weightage for one particular item. Like if we say, or else we can use a folder which has both idli, dosa, or vada for training purpose. So combination of three.
And then what will you call that?
We'll call all the three items are present in that.
Oh, there is idli, and then if in all three other idli, dosa, vada.
Yeah.
Interesting. Okay. Okay. Anyone else? Jose, what do you think, Jose?
I have no clue.
So means like anyway we'll be predicting, we'll be having results to analyze whether it will be a idli, dosa, or vada, right? So we'll actually get three outputs also, right?
Okay.
And if we are actually able to have a threshold or some kind of a saying, okay, if all these three things are actually more, it's like positively correlation, something like that, right? That's whatever I'm trying to mean. If it is there, then we can actually say. So some kind of a threshold to say like the presence or not presence of this particular stuff.
You all have smartphones, right? I'm assuming all of you have smartphones, and you all take a lot of pictures. Like when you take picture, point at someone, what do you see?
Recognizes the face or something, like any part.
Features,
Especially,
something like
yeah.
that.
Taking this, I'm sorry, VC, what did you say?
No. Picks out on some feature,
Picks
some
up
contrast
feature.
perhaps.
Okay, it picks up face, as Pradeep told, right?
Yeah.
So it always, what does it do with the, how does it, like after it identifies the face, what does it show? What does it do?
It puts a box.
It puts a box. Good, Abhinav. It puts a box on the face, right? How does it work?
Even detection.
What?
It detects it's a face based on the shape, right?
Okay.
And then maybe some smartphones will also say that, you want to focus only the headshot, or like which area you need to focus on.
Actually, if I'm not wrong, it convolutes and extracts the features and some kind of.
Not giving that up, no, VC. It's like
Too much of deep learning work.
no. Okay, no. It does. Okay, so if Abhinav, if that's what is happening, why didn't that work for idli and dosa?
So that it didn't give the correct convolution matrix still.
No, Abhinav, this one, the no. Okay. So think. Who else is awake?
Okay. So can we like
wait. Sundar is telling something. 1 minute.
Okay.
We can touch on this multi-level classification, right? Because in camera, when you have 3 people, the bounding boxes will be happening for all the 3 people. So in the same way, when you have in a plate, when
How
you
does
have
it
both
happen?
idli and
Okay,
dosa.
sure. So what is that called? Okay, good. What is that called? Okay, good. That's correct.
Sorry, what did he say? Say that again.
Sundar, go ahead.
Can you say that again, Sundar? Yeah.
Yes, it's about something like a multi-level classification, like detecting every object that is classified in our training model, training set.
Oh, multi-label classification. Okay.
Yeah. the same image will be it will be classified. It contains both PG and those.
Oh, okay.
Okay, now, Anand, how does it work, Anand?
Multi-label classification.
Label classification. Oh, that's what Sundar is telling, no? Okay, so we have seen.
No, ideally, when an image is, sorry, someone is on speaker.
No. Okay.
No, when we take an image, right, it will ask us to tag, right, to recognize each person. So let's say I will tag as me and my kid name Sneha or whatever it is. So next time when we try to take a pic, maybe it is identifying basing on that.
Okay, so we've seen what regression is, and we've also seen classification. What's the difference between regression and classification? Sandhya, what's the difference between regression and classification?
Regression is for continuous. When we train a model which gives continuous result, like stock market price prediction, it comes under regression model, and the sign data points prediction we did is also a part of regression, but the Italy dosa vada, it comes under classification. Since it classifies the images into Italy, it's not continuous, right? It's, this is the difference between regression and classification.
Okay.
What else?
Okay, it's okay. Yeah, sure. So regression is where your target that you're predicting is continuous in nature. When it's discrete, it's classification. And we're introducing a new class of problems, which is called object detection. Okay, when you have multiple objects in your multiple points of interest, multiple features of interest in your map, and you want to identify them, right? So that's another class of model called object detection. Okay, so we are in we've done regression, classification. This is a new class of model, object detection, which is what you would see when you have multiple things. So this is simple. Classification would be trivial in most of it. If you want to do in computer vision, if you want to do, there's a lot more object detection that you have to do. And this could be like in an image, or any video that you take has things that keep moving, and you need to identify what's happening. So that's all object detection models that you would do. Just introducing the concept here, we'll go and then build some of these things out. So who else is working on Idli Dosa apart from Vidya? Is anyone else working on it?
Actually, I was working.
You were working? Okay.
Kyle was also working. Kyle Vidi.
Okay, so next class Kyle will present, okay, what she has done.
Hey, Kyle, when do you have an exam? Your next exam?
Friday, we see.
Friday, all right.
Okay, we'll pick it up. Okay, after your exams. No, not during the
exam. Let's leave them for the moment.
Let's leave them. Once all your exams get done, we'll do it. So then we'll.
I think most of your exams are done by this week. Is it most, if not all? Is it right?
Actually, for us, the exams are December.
So. Yeah, okay, that's instrumentation. How about computer science and EC?
The technical papers get solved by this week, and English paper is on next week.
Okay, English. All right. How about Sandhya? How about your case?
Next Wednesday we have an exam, and after that there is a 15 days break, and December 20 we have our last exam.
Next Wednesday. So next Wednesday.
Next Tuesday.
Oh, okay. Next week, you mean?
Yeah.
Oh, all right. Okay then. Okay. Fine. Sorry, Bhargav. Over to you.
Okay. So we'll do. That's my train of thoughts. Okay. We'll do that. Okay. So Vidya and Abhinav. So one, you've done only, so Vidya, you need to get more data.
Yeah, sure.
Okay.
Yeah.
10,000, it's
Mhm.
trivial to scrape. Go use a plugin, download. There's no getting away from manually curating the idli and dosa.
Yeah, that actually took me a lot of time.
But let's
So
not invoke what Srisha wanted to do. Cook so much and give. Let's just go and then curate it. Please do it. It is part of doing a project, right?
right,
Nothing is
right.
easy. To do interesting things, it requires some amount of boring work also to do. So please go do it and then go do it. The other thing that I wanted to do, I think you're still on, I don't know, some pre-trained mode. ResNet 50 is what you're still on. Did you go build a vision transformer model yet?
No.
Okay.
No.
So let's start doing that. But you can't do it until you download like 10,000 images.
10,000, yeah.
Download more images and then do it. That's true. That's for you also, So just go and then do it. We'll do, and then all of you should catch up to it. It's not like there are only 2 people who are presenting all of it. Want all of you to present, so you need to go and then do it. The other thing is, where is Naveen? Naveen had done something interesting on linear regression, so he'll present for like 5 minutes. What's some interesting thing? The same thing, but he has written code. Whatever Abhinav presented, he also has a code to go over it. So let's just see it for some time. You're on mute, Naveen. Can't hear you.
Okay, is my cursor visible?
Yeah.
Okay. The idea is like I thought of, okay, like I've done a lot of linear regression using scikit-learn. So whenever I get data, I put it I put in scikit-learn and I'll get an output. So I thought, okay, let's derive from the base. Like I will be able to derive it. That was my first question. I was trying to do it for logistic regression. I thought, okay, we'll start with linear regression. So the idea for us, I derived the equation, I implemented in Python. And the second part is for gradient descent, I want to visualize how the line minimizes the error. So these are the 2 things we'll be seeing. So first part I'm importing. I'm taking a simple equation, nothing complex. So I've defined my error functions here. Here I'm taking a simple equation, which is like I plus 3. This is my x, and I'm just multiplying it by 4. So that is my y. I have here my slope is 4, my intercept, y-intercept is 3. So this is all my variable. I need to go predict it. So, okay. Again, now like my output need not like to be the same value, 4 and 3. It can be a different value. Still, I'll be able to achieve that particular line. The reason is it is confined to only that particular range of data. Okay. So now let's say I'm going, like I'll do, this is my actual equation, right? So I have some randomness in it. So here and there, and this is my actual equation. If you see here, this is y actual is I star 4 plus 3. This is my actual equation. I'm plotting it, and my R square is 0.99. Okay. And let's come to the mathematical approach. I have a lot of derivations. I'll share this on GitHub. So please feel free to look in. So here, this is our base equation, and here is our loss function. So if you derive it, if you take partial derivative of both C and M, you will end up in this equation. Okay, C equal to this, M equal to this. If you further like solve it, you will get a place where it will be like covariance of C and M into variance of M. It will be something like this. Okay, this will be our end equation. You can still dig in further deep, but like this is more than enough for us. Okay, now like just go. This is like it may look scary, but trust me, this is a simple derivation. Okay. Yeah, now what I'm going to do is I'm defining a function. Okay, here this is my numerator, which is like a covariance of x and y. So here xi minus x mean, yi minus y mean divided by denominator, and I have the denominator. And now I know what is my m and what is my c is. Okay, this is my, here b is m, sorry for mismatching all the variables, but here b is m, sorry, here, yeah, just give me a minute. Oh, yeah. So here I have the, let's not consider as M and C, let's take like weights and biases. Like let's consider these both are the weights. Now I'm printing the weight. Okay, so now I know 4.103 and minus 9.8996. Let's plot and see whether this is right or not. If you see here, it goes in the same straight line equation, and our R square is about 0.99. Okay, it may not be the constant, like both M and C may not be the same as our initial equation, but still we are able to achieve this. Okay, maybe if you put some out of range values, it may go off. Okay, there is like little chance for it, but yeah.
Sorry, what is the data set you have taken?
It is nothing but like a simple equation where here it is, right? So it is I star 4 plus 3. Basically, I took from 0 to 10, and I have added plus, I have multiplied by 4, and I've added plus 3. I've moved the equation a little bit up, and for each x, I have multiplied by everything by 4.
You've also added some noise, right? Because otherwise it will be a perfect straight line, right?
Yeah, I've added some noise here, yes.
All right, okay.
Okay. Yeah, for any, let's say any one one independent variable and a dependent variable, if you want to fit y equal to mx plus c, then this is the ideally your equation, right? So you need not to do anything else. You need to compute just mean, and you have to pass through this particular derivation what you have here. Okay?
So the num plus, so that's your covariance, isn't it?
Yes, that's my covariance.
And the 10 is the variance, right?
Yeah.
All right, okay.
So I'm passing it through each and every values, then like taking that minus mean. Like,
oh, okay. So basically what you're doing is you're calculating the B in the above screenshot, right? Covariance of XY by variance of X.
Yeah, this is
that's
that's it. That's it.
Right.
Then here I have my weights, right? So M and C. So
yeah,
I need
and C here is, if you just scroll a little above, I think you'll have an equation for that.
You have it here.
Yeah, y hat minus. Okay, yeah.
Y hat.
Not y hat. That's the average, right?
Mean of, yeah.
The mean. Okay.
Mean of y minus
b times mean of x.
So here, like by derivation, you achieve like the utmost the straight line. Here, the computation is too less, and like maybe it ran in 0.1 second, so it is so quick. So also I tried, okay, why not go use gradient descent for it? Then I started deriving the equation for it. It is so simple. So when you take a partial derivative of the loss function with respect to m, this is the equation what I end up in. And if you take a partial derivative with respect to c, this is the equation what I end up in. It's like a simple partial derivative. It will take like 2 minutes to understand for you. Then here what the update comes, like Abhinav discussed, right? So this is my initial weight. Then what I'm doing, let's consider this as one step further. M on this left-hand side is one step further. This is one step. This is the current step. What I'm doing, I have a learning rate, and I'm like I have taken the partial derivative of this, and I'm multiplying that by learning rate, and I just minusing it. Okay, and this gives my MNC for each and every step. Let's consider like I'm running it for 3000 steps. Okay, let's see how would I. This is the same thing again. I've used that particular formula here. This is the derivative of M, and this is the derivative of C. Here I'm updating MNC. I've declared MNC globally. Okay, and this is my learning rate.
So you didn't use the library that allows you to pass a function and get a derivative out.
Yeah, it is SciPy does it. I have tried it, but it gives the derivative of it, but I just want the value of C and M here, right? So
right, okay.
Yeah, like for this, yeah, it makes sense, right? So yeah, that gives actually it gives.
Okay.
SciPy or something. SciPy, like their version of SciPy.
Yeah. I've used it sometimes. Okay.
Or something. I've started with that, then I thought, okay, let's derive it and see how it comes.
Yeah.
Okay. Now what I'm going to do at each step, I'm going to print this derivative of first derivative of M and derivative of C, so that you'll know how it decreases. And also I'm going to plot the mean square error in a graph, see like first where it is and how it is reducing. So you can take this as a direct example for gradient descent, what we have seen here, what Abhinav have showed us. Okay, there's some plots here, nothing much. What I'm doing, if my accuracy didn't improve like beyond 0.05 or 100 epochs, and then I'm breaking my computation. Okay, let's see.
I think Bhargav would want you to change epochs to iterations, perhaps.
No, yeah, we'll have a conversation around it. Okay, I think I should play it slower, right? So
Yeah, please. Little slow.
it diverged to the max. Let me rerun it again. Okay. If you see here, first our equation is here, then it goes on getting here, or automatically our mean squared error keeps on reducing. Like at 16th epoch, like our R square is about 87, 88. And if you try beyond that, it goes here. If you see minus 7.8, this is all our gradient values.
So for your algorithm, have you stopped it on the with the number of iterations, or you chose to look at the R square?
Yeah, if the R square haven't improved beyond 0.05 for 100 epochs, I'll stop it.
Okay.
This will get stopped around maybe 120 or something. By the way, like it won't be same. If you see here, like all my first order derivative value, still it is not 0, right? So I have certain value here, but my model haven't improved after that. So considering this as my global minima, I'll stop here. No improvement. Yeah, it will stop around 120 or something. Yeah, it got stopped. So at 1112 epoch, it got stopped, and my R square is around 0.9. And this is my final equation. Here is my M value, here is my C value, and here is absolute error, here is squared error.
Wonderful. So you never tried this before, the first time, is it?
Like I've tried gradient descent using PyTorch, but I haven't coded from scratch. So I'll tell you, I'll stop sharing and I'll tell you what is my takeaway from this class. So I've done most of these things, but I've used all scikit-learn and stuff. I always thought, okay, we should learn math, and I never did it because like when you start working, right? So you have to do I never come back to machine learning, right? So it is almost that whatever I do, everything goes on deep learning, but always I wanted to mathematically solve it. And this class really helps me. In last 2 days, I've learned a lot, right? So I revisited all my matrices. Then I started learning determinant. I went crazy. So I have like 20 papers here. It's full of derivation. I do it back again. It is fun.
Hey, question. Yeah, again, I mean, I'm a duffer when it comes to this. So you use the terms machine learning and deep learning separately. Why is that so? You're saying you don't do machine learning, you do deep learning. Why is that so?
So like most of our what we do at 5C is like we interpret with images, right? So
but what's the difference between machine learning and deep learning?
Yeah, machine learning is like you learn anything on a tabular data, or the data is structured, right? Where in images it need not to be the same, right? Let's take in deep learning you have computer vision and you have LLMs. So there is no structure of certain particular data. What do I mean is, let's take an example here. Let's take a tabular data. If this is age, this is going to be only the age. Like income cannot come in that particular age, so that is defined. But in images it is not defined, right? I cannot say on 24th cross 28th pixel it will be always representing a ear of a cat. I cannot tell it. There is no representation for a particular feature telling that okay, this is where it is going to be. That's one huge difference. So I'm excited.
So it's like saying deep learning would unearth patterns that you don't know. Is that so? You may not know.
Patterns? You may not know.
Right? But machine learning, you kind of know what you exactly want.
No, it is complex, right? You cannot visualize it, right? If it comes to let's say 10,000 attributes or 10,000 features, right?
Okay.
You cannot visualize it. Let's take 20 years of data. It's very hard for you to visualize it.
Okay, cool. Bhargav, over to you.
Naveen, if you don't mind, can you please share this?
Sure, I'll do it. I'll upload it in GitHub and I'll share it.
Thank you.
Shirisha, your microphone isn't close to your mouth.
Sorry, actually.
Yeah, we understood. We understood what you said.
So, someone's supposed to do logistic regression from scratch, no? Who's going to do that?
Nobody yet. We'll have to find somebody to do it.
Okay.
No one is taking up, I can do it.
No, let someone else do it. I know you can do it.
Actually,
I
wanted
really
to.
like what Abhinav
You want to
did.
try, Shirisha?
Yeah, I wanted to try.
Okay, give it a shot.
Yeah.
Maybe
Wednesday.
time will be short next week. Monday.
You want time?
Yeah, sometime. Not
I
possible.
need someone to do basics of linear algebra.
Linear algebra.
No, I think we are hitting a level where I want, if you want to, so when I started, I didn't think we'll go into the math part of it, but if we're covering the math part of it.
But Bhargav, don't we need to? What do you think? Some math is needed, right? I simply can't avoid skirting math.
It's one thing is to, you don't do all of this in, okay, it's good to know. If you're doing it, let's do it. But if you're going to do any further, then knowledge of linear algebra is important. I need someone to take it up and do it.
Again, folks, those who want to do linear algebra, you don't need to pick up any book. Just go through 3 blue, 1 brown series. That's generally sufficient, to get the intuition behind.
For intuition, but if you want to solve, so we saw, okay. So we had Abhinav solve linear regression through gradient descent. Linear regression can also be solved through linear algebra. So I need one of you to teach that in next session.
Gradient descent using linear algebra, right?
Linear regression
Sorry,
using.
linear. Yeah.
Wanna try?
I'll do that then.
Okay, good.
Next session, Wednesday. You know linear algebra, confident. You're confident.
Yeah, confident. I'll try.
It's not linear regression would not be very difficult. Just a bunch of matrices and determinants, and that's about it. Class 11 kind of stuff. Again, try it out. Want to try?
Yeah, I'll try. Actually, I have seen that. Actually, like I'm looking through the math part only.
Yeah, right.
Yeah.
What we had did in matrix format, am I right?
Yeah, correct. Yes.
Yeah,
Correct.
matrix determinants.
Calculate inverses and stuff. Like
Inverse and transpose, inverse multiplication and all. I've seen that actually.
Yeah, but the thing is, you'll have to tell it in a way people understand.
Yeah, sure.
Right.
Yeah.
Understood.
And if you think there is any pre-reading that people have to do, just send it in the Telegram channel so that it doesn't look like Greek and Latin for us. So Shirisha, if you think that we need to do some pre-reading, please send it across.
Sure.
Okay. It's a bunch of things. We also need to do some introduction to programming for everyone.
Yes, you need to. Okay, I mean, Chandralekha, I don't know whether she's there. She asked a question. She doesn't have programming background.
We're doing it. It's part of that will do. Anand will do it. But Anand got back only today. So
okay.
And he's again traveling. So probably next week.
Coimbatore, is it?
Yeah. Yeah. Anand will teach Python for us, but that's probably next week. Okay.
Yeah, Bhargav, you wanted to cover me on that variance. So
yeah, sorry. I had something for you. I was thinking, what did I tell you to do? Go for it.
Yeah, I had a maybe I need to present something and see like if I'm just going in the right direction or not.
Yeah.
To take some feedback from you all.
Done.
Okay. So can I do it today or Wednesday is fine?
Yeah, let's do it now. Is it okay if we go 5 minutes, 10 minutes? How much time do you need?
I'm just going to share what I have because I just put up something.
Let's do it.
Yeah. Okay. So went through grade 8 max to understand what variance is to begin with. Let me share my screen.
Is that a Mac?
Yep.
It's a Mac.
So I just started off with the high school math, what a variance is, and then I will slowly transition
Can you
to.
make it larger? I really can't see it.
Oh, you're not able to see it. Okay.
No, it's too small.
I don't know how.
I'll just present it.
You can present it, right?
Yeah, so much better.
Okay. So I just want to briefly touch on what variance I understood because I really need to refresh what it meant. And then slowly I just try to fit in like how the variance that we studied in Max in the class 8 or class 11 applies to machine learning. So a basic definition of variance is you actually try to determine how the data set vary, like how the numbers in a data set, right? So how it kind of varies to the mean. The formula is basically this. So I'll just take you to an example that I tried. Okay, so this is where I try to just put in something where how the degree of dispersion.
Let's be on the slide, please.
Okay, yeah.
And let's build an intuition for what. Let's come to the formula later, but let's understand the purpose. Why do we need to compute variance?
So it helps understanding the data set that we have, how dispersed it is. And we want to find out like, maybe that's how I understood. So how to understand the data set that was presented to us, right? So between two different points, like how dispersed it is. So that's a basic reason why, like, we go for this variance. So we will start with like how the mean, and then how mean is important to just derive the variance. So how we can just derive the mean for a given data set. And then I'll see like, that's how I understood. So we just calculate the mean for a given data set, and then you calculate the variance from out of it. And then you make some interpretation based on the value you get for a variance. So so this is basically like,
You have okay. So is your formula for variance correct?
Variance is, yeah. So in here, the sigma square. Yeah, it's actually square.
So it's basically the data point minus the mean whole square, the sum of all of it divided by n, the average of it, right? That's what you're telling us, this variance.
Yes.
The question that I have for you is this the only formula for variance?
No, there could be more than one formula for variance, but this one I just narrowed based on the understanding I had. There could be one more formula. There is something that I saw like n-1, 2.
So that's what. So why is it n-1 and n? What's the difference?
I haven't really thought dig deep into that, Bhargav, but I saw there is a difference variance formula too. So that's a takeaway question for me.
Okay, understood. Okay.
Yeah.
Got it.
So basically, they call these distribution as like, you know, when we take a data set, they call the data points as population. So I remember, like you said something about the population when we talk about our data points. So it's on one population, you just determine how does it deviate from the average mean. So that's basically like, you know, this example that I'm going to show is going to probably tell you, like, you know, how dispersed the data sets are between two examples. There is a data set A and data set B. And when you calculate the variance, you will understand how dispersed the data points are to the mean. And you understand, like, you know, how this can be like incorporated within regression, like the regression models. So with this concept, maybe we can go on to the machine learning part. That's how, like, I related how the variance is used in machine learning, as how we during the earlier session, Abhinav talked about MSE. So those are actual premise of like using the variance. How they use the variance in machine learning is by calculating some values called MSE. I'll talk about that. But I just want to take a pause here and just make sure my understanding is right about the variance part in machine learning, Bhargav.
MSE mean square error is not variance, no?
No, the concept of like variance is being used in MSE. Is my understanding right?
Why?
No, it is used in R square, right?
It's used in R square. Okay. So maybe I have to just, you know, I have to put in some Bayesian understanding here. So I need to relearn and make sure my understanding and correlation is correct. Okay. So that's the premise I made when I was just running through the variance. You know, what we studied in class 8, like how we can just correlate that with machine learning. So that's how I just made this presentation. So that's why I wanted to understand, like, you know, should I go through with this flow or have to just make a different presentation or something. So that's when, like, you know, I tried to understand, like, took a 2 data set and calculated the mean. So mean is nothing but, you know, you sum up everything and divide by 5, and then you use that mean and just to create the to find out the variance, you just use this formula. And that's how you kind of find out what is how dispersed my given data points are. And with that, I will just switch on to the next slides where we can just incorporate this in the machine learning. So that's what I basically thought would be the hold on. So the variance in machine learning, so it quantifies the variability of the prediction made by the model. And when you calculate the variance, like the high variance model tend to overfit the training data. If there is a low variance, then the model may underfit. So so basically what it helps is to understand the how you can tune the models to the right level of complexity for a given problem. So that's the essence of, like, you know, predicting the variance. That's how the role of variance will help you in your prediction models. How we do it, I thought we will be doing it by calculating the MSE value. So that's what I thought. I'll just go through some questions that I've asked in ChatGPT. So I went through Khan Academy to just understand this. So this is the statistics and probability class 4 for grade 8.
Common measure of spread, range, interquartile range.
Yes. So variance of a population. So it's actually a good refresher of, like, understanding the different parts of, like, you know, how this all can be related. And then I also tried something to just understand how the variance will play a factor, like, based on the MSE model. So now I think I need to just revisit my learning, because Naveen said it's R square, not MSE. So I just try to.
This is just your error prediction. Variance is not that, but okay, good, interesting application. One I can tell you right away. And Kyle is also messaging, so I'll tell you. You should use n-1 for variance. So that's
Okay. Okay.
So tomorrow, next class, you'll tell me why we should use n-1 or not n.
Yeah, he spoke about Khan, Sal Khan talked about n-1 in his video, so I didn't cover that part. Yeah, I'll try
It's
that.
not, I will tell you a hint. It's nothing to do with sample versus population. Oh, sample, I have to use n, population is n-1. You will never get, or population is n, sample is n-1. You will never get population ever. You will only be working in samples. But why do we need to use n-1 and not n? So they read about it and then tell. We see, do you know why n-1 and not n in denominator?
Just taking a guess. I think n-1 will be the best estimator for the population variance.
Why? Correct, but why?
Degrees of freedom. Just taking a guess.
Yeah, that's right. Okay, good.
Sorry?
Didn't expect you to tell. Yeah, that's correct. So now, Pradeep, you'll go learn what VC taught and why that's the case and how that works.
Sure, Bhargav. Yeah. I'll revisit my learning. So that's why I said I need to make sure I just follow it along. Yeah.
Good. Okay.
I'll stop my share. Yeah.
Anyone else has questions? Yes.
All right. If there's nothing else, I'll stop recording.
Okay.